Yuto, are you ready?
Yes.
Let's get started. So welcome to the algebra geometry seminar. Today we are very happy to have Yuto Yamamoto from Riken in Japan. So he will be visiting here for the whole week, and his office is in the Astromas building, fifth floor. So if you have any question and if you want to discuss with him, so he will be here for the whole week. So today he will talk about period integrals of hypersurfaces via tropical geometry. Yeah, please.
Thank you for the kind introduction, and I'm grateful for the invitation and the opportunity for presenting my talk. And it's also honored to be here, and I'm very excited, particularly because this is my first time to visit Taiwan. So in this talk, I would like to discuss periodic integrals in complex geometry and from the viewpoint of tropical geometry. And my plan is maybe in the first 30 minutes, I'd like to give a brief introduction to tropical geometry. I will explain the very basics of tropical geometry. I hope it will be accessible to everyone since it is kind of elementary. And then I will move on to the discussion on periodic integrals or hot structures. Yeah, maybe in the latter 60 minutes. So that's my plan. And needless to say, please feel free to interrupt me at any time if you have any questions, comments, or corrections. I will appreciate them. Okay, let me start. So with the so in tropical geometry, we often consider we work in the following setup. Let K be the uh, the convergent Lorentz field. This means this is a field of Lorentz series whose positive index part converges at some neighborhood of the origin, and we also suppose that the negative index part of it has only finitely many terms, and this has the standard valuation which I will write as the var. It's a map from K to Z or infinity. Is given by and X is the indeterminate. This is mapped to the minimum index J such that the corresponding coefficient Cj, so this is an element in C, is not equal to C. So, and this is and we take a polynomial over K if K and y1 m1 da 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 y plus 1 and e plus 1. So this is a Roland polynomial over K in e plus 1 variables. So here, this is an element in let me write in this way. So A and A. Where A is a subset of C to the D plus 1. And here is definitions. The tropicalization, it is sometimes written as trope of F. This is a function on R to the D plus 1. So the D plus 1 is the number of variables. Is piecewise affine function defined by the following formula. Okay. These capital Y's are the coordinate on this R to the D plus 1. This is the value at this point is defined by the minimum of the variation of Km plus M1 minus Y1 plus YD plus 1. So what we are doing here is basically to replace this sigma the sigma with the operation of taking minimum, and the Km turns into the valuation, and this part is replaced with this one. And each of this term from here to here, this is a piecewise affine function on R to D plus 1, and there are possibly several those monomials, and we take the minimum of them. So in total, this is a piecewise affine function on R to D plus 1. And this is the tropicalization and the tropical hypersurface. This is a subset inside to the D plus 1 is defined to be the corner locus of this tropicalization. I would like to give you an example. For example, let's say F is given by 1 plus Y1 plus Y2 plus X over Y1, Y2. So this is a polynomial in 2 variables. Then so we can tropicalize it. So the trop F is now given by, so this is a function on R2, and Y1 and Y2 are coordinates on it. It's a minimum of the following terms. the 1 is replaced with 0 because the variation of 1 is just 0. And y1 and y2 replaced it with capital Y1 and Y2. And the variation of x is 1. So let me write 1 here. And Y1, Y2 turn into minus Y1, minus Y2. So this is a function on R2. So let me write R2 here. So it turns out that the so this function is a function on here, but it turns out that corner logs of the function is the union of these yellow lines. Sorry, this point is 1, 0. This point, and this is 0, 1. This is origin. This is capital Y axis, and this is Y2. And so it turns out that this function coincides with the constant function 0 in this on this triangle, and it coincides with the linear function y1 on here, and coincide with the function a linear function y2 here, and similarly here it is given by 1 minus 1 y1 and minus y2, the last term. And so there are this so on this on each region that there is some monomial that attains a minimum of the tropicalization, and when we cross one of these yellow lines, the monomial that attains minimum changes, and so that is why the corner locus of this function is exactly the union of these yellow lines, and this is why this is V2F. A tropical hypersurface defined by this tropicalization. So in this case, that this tropical hypersurface is a graph sitting inside R2. And I have one remark here. This is actually dual to the somehow dual to the Newton polygon. So when we consider Newton polygon of polynomial this f, one corresponds to the origin, and y1 corresponds here, and y2 corresponds to this vertex. I mean, this is also in R2, and last monomial corresponds to this point. And 0 corresponds to this vertex, I mean lattice point, and y1 corresponds to this point, and y2 corresponds to this one, and this one, and this one. So in this way, somehow this figure and this figure are dual. And this sometimes helps us how to see how tropical hypersurfaces look like. And so actually, such a polyhedral complex, the tropical hypersurface, or more generally, tropical varieties, allows us with the limit of a family of complex algebraic varieties. And I would like to discuss a little bit about the relation between them. So in order to do that, we take a positive real number, let's say t. We suppose it is small. And for T, we substitute T to the indeterminate X in F. Then we get the Laurent polynomial over C. So please remember that we suppose that the Laurent series is convergent. So substituting small real number to the indeterminate, it makes sense thanks to that assumption. And we now have a polynomial over C. And we also consider a hypersurface defined by the polynomial T inside the algebraic torus. So every time we fix an element T by substituting like this, we get a polynomial and a hypersurface defined by it. So we now have a family of Laurent polynomials over C and complex family of complex hypersurfaces. And we consider the logarithm map. Is the which is a map from system to the D plus 1 to the D plus 1. So for each component, we take the absolute value of it and take the logarithm whose base is T. And here is the theorem. This would be one of the most fundamental theorems in tropical geometry. So we consider the limit T approaches 0. The limit of the image by the logarithm map of the hypersurface DT in the algebraic torus. And this actually converges to the tropical hypersurface defined by the tropicalization of it. So this is a claim. So what is saying? What this theorem is saying is like, for example, let me go back to that example. For example, in that case, so let me draw the figure of this log T, the image of the ZT by log T. It looks like amoeba. So since we are taking the image by this log map, so this is a figure in R2, and so this is exactly the ambient space of the tropical hypersurface. Tropical hypersurface is sitting here, and we are now comparing the tropical hypersurface and the image by this map, the log map, and so this is the log T. So every time we fix an element T, we get such a picture, and when T varies, then of course this figure also varies. And the theorem says that when T approaches to 0, then the amoeba shaped figure gets skinnier and skinnier, and eventually it converges to that spherical curve, the union of the yellow lines. So this is what this theorem is saying. Well, so we first take the absolute value of the coordinate, and we take the value of the logarithm whose base is t. Are there any other questions? And we will actually use the idea of the proof of this theorem later when we discuss the purely integrals in this talk. So let me briefly explain the briefly explain how it is proved. So I give you a sketch of proof. By the way, this figure, so the image by the logarithm map of the hypersurface is indeed called amoeba as a mathematical term. It is called the amoeba of ZT or amoeba of FT. Anyway, so in order to prove it, so we do in the following way. So first we fix an element of the target of the logarithm map. And we consider the free image of this point by the logarithm map. So this is a subset in C to the d plus 1. And here we have the following experiment. We have the first, so this is trivial, but the one of the coordinates yi is the order of the e to the yi, capital yi. So this is kind of obvious. This follows just from the definition of this map. We took the logarithm whose base is t of the absolute value of the coordinate, and so yeah, obviously we have this one. And from this, we can also get the am y. Maybe this might be confusing. I mean, so this maybe it's okay. So yeah, this is one of the point, and so each coordinate is fixed. I mean, the value of the coordinate is fixed, and maybe not. This is not very confusing, but let me just mention. So this part will be I will abbreviate this as the ym, and so this part is also will also be written as the just capital Y, and for this part, I should have changed the color. This part will be written like M times Y. Yes. And so we now look at the one of the monomials containing in the F. So we also have the estimate of this the order. It has the order of T to the evaluation Km plus M times Y. So regarding this Km, so it turns into the T to the power Km, but this is just I have maybe erased, but this follows just from the definition of the standard valuation, and the latter part, Y to the M part, turns into this one. But this just follows from this one. So this is also kind of obvious. And we can also see that the monomials such that the corresponding to the power K as my coincide with the value of the tropicalization of it at Y. Our reading terms. The OVFT. So we are now thinking the limit as T approaches 0. Yeah. So the monomials whose the power of T is the smallest gives the leading terms of FT. And in the definition of the tropicalization, the trop F, we took the minimum of these tropical monomial. So that is why we can see this claim. Let me see how I can explain. So actually, by using this observation, so we can somehow approximate the polynomial. Let me explain it with this example. So for example, let us look at this region, the neighborhood of the origin. On here, according to this observation, we can see that on here, among these monomials, so let me say, so now I have a substitute T into X, and now we have a polynomial over C. And then, for instance, around here, FT is approximated by 1 plus Y1 plus Y2. Because on here, in the tropicalization, 0 and Y1 and Y2 attain the minimum. so which implies that FT, the leading term of FT at around this region are Y1 and Y1 and Y2, and the last term is smaller. Similarly, for example, if we look at around here, then so the FT is approximated by 1 plus Y2, because along this edge, 0 and Y2 attain the minimum of the tropicalization. So Y1, the corresponding monomials 1 and Y2 are leading terms. And lastly, let me also take a look at here. So it's a little bit far from the tropical hypersurface, but on here, there is only one monomial, the capital Y2. I mean, the only one monomial that attains the minimum of the tropicalization. So, so FT is approximated by Y2. So in this way, we can, if we locally look at the tropical hypersurface and the pre-image of that region, then we can, on there, we can approximate the polynomial FT. And the last one is a little bit special in the sense that this cannot be 0. We are working inside the algebraic torus, so and the coordinate cannot be 0. So and this the leading term cannot be 0, and so of course FT can also not be 0. But on the other hand, these two cases, there is more than one monomial, and so these can be 0 for C, because since there are several monomials in the leading terms, so they can cancel each other out, and so the situation differs depending on whether there is only one leading monomial or multiple. And so, and this is also the reason why the image by the image of the ZT by logarithm map T looks like this. So the points inside this are distributed just around the tropical hypersurface. And this tendency gets more and more extreme when T approaches to 0. And this is basically the proof of this theorem. So what we are doing is, so this is a figure in R2. So this is a target of the logarithm map. And we take some small region like this one or this one or this one. And we consider pre-image by the logarithm map, which is a subset inside C star to square. And so that is what we're building. And this idea will also be used in the computation of periodic intervals. Are there any questions? If not, I would like to move on to a discussion on periodic intervals. What I would like to discuss in this talk is rather computation of asymptotics of period integrals of family of complex varieties than a period integral for a single complex variety. And one of the motivation comes from the gamma conjecture. So I would like to briefly recall the gamma conjecture before discussing the tropical computation of period integral. Okay. So the situation or the setup is like the following. So first, suppose that we have a symplectic manifold, Calabi-Yau manifold. With a simplex structure. I mean, omega is a symplectic form. And we also suppose we have a family mirror to this X omega. So this is T is a parameter, and it's a family of Calabi-Yau manifold over a punctual disk. And we take a cycle CT inside ZT. Lagrangian cycle of this ZT, and let E be a on X mirror to the CT cycle. Interactive. So probably I should write like polarized. So we need to so we suppose that we have so this has a symplectic form so that these two are mirror. So and probably I can say that so that is also so how we should take the polarization is also a part of the problem. I mean, in the mirror symmetry. And the claim is the following. So we consider the periodic integral on on for this ZT and consider the asymptotics of the disk period integral as t approaches 0. And this claims that it is described in terms of the mirror Calabi-Yau manifold. Right. maybe I should erase this one. Where the with this is a continuation of that board. Yeah, omega t is uh, homomorphic more informed. On X. Sorry, no, on Z3. And that gamma X is the gamma class of the X, which is defined to be the product of gamma 1 plus delta I, where delta I is the, the channel of X. So this is a class of homology group of X. So we also have a more explicit formula. It is written in the form exponential minus gamma C1x plus E minus C K minus 1 factorial and Px. Gamma is the Euler's constant, and zeta is the Riemann zeta value. Anyway, so it's the homology class of X. So we are now thinking of the one parameter family of Calabi-Yau manifold and the period integral over some cycle. And the claim says that it is the principal part of the period as t approaches to 0 is given by it's written in terms of the mirror Calabi-Yau manifold. And what I would like to discuss next is the following result by Abzaid. Manatula, Iwitani, and Sheridan. Please let me abbreviate it as AGIS. So it says that one can compute the asymptotics of the period integral maybe I should in some particular case. In a case where X and Z T's are mirror pair of Calabi-Yau hypersurface. This of Patirev. And CT is a cycle. Lagrange cycle mirror to ambient line bundle. The Calabi-Yau hypersurface of Patirev is already the Calabi-Yau manifolds sitting inside the toric variety, and so the ambient line bundle means that the line bundle coming from the ambient toric manifold toric variety, and we suppose that it's mirrored. The cycle is mirrored to that ambient line bundle. By using tropical geometry. And one can actually confirm the gamma conjecture for this case. So that is the claim of the theorem. And actually, what I would like to, my goal of this talk is to review their work and discuss the generalization to the case where the hypersurface may not be Calabi-Yau. And so if are there any questions? First, fourth line. Uh, 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 so probably I should have said that the degenerating family at the point. Sorry, so this is maybe misreading. Degenerate family at the, I mean, sorry. Thank you very much for the comment. You mean this part? Sorry. So this is degree of the cohomology group. So this is a pairing in between the cohomology classes of X, and the degree means that the degree of the cohomology group. Yes. So yeah. Yeah, this is maybe too sloppy, but yeah, we need to take the scalar product appropriately so that this holds. But yeah, maybe. But basically, when if we only consider the period integral for a cycle, then the what matter is just the homology class of it. So actually, so in that sense, the being Lagrangian is not very important, at least in this conjecture. Sorry, but this is I am sorry. This is epsilon. Some positive real constant. Positive yeah. For some epsilon, yeah. So this time vanishes when t approaches 0. So I would like to briefly explain the idea of their computation and before discussing the generalization. So in order to do that, let me again consider some example that is probably better. So first, I would like to fix the Newton polytope of the the polynomial. Probably the simplest one is so this is a figuring three-dimensional polytope, and so distance between and this is the origin, and all the other points are the distance between the origin and other points are all one, and so this is a reflexive polytope, and I would like to consider for this case, ft is given by -1 plus. Let me write this polytope as delta. E to the e times y and s. And then the tropicalization is given by minimum was 0. -1 turns into 0, and other terms is like 1 plus minus y1, 1 plus minus y2, 1 plus minus y3. And the trophical hypersurface defined by this looks like this is also figuring R3. So this is the figure of V trophy. So this is in this case, this is a two-dimensional polyhedral complex sitting inside R3, and so it's an union of the boundary of the central cube together with unbounded facets, these ones. And we consider the cycle given as the positive real part. Zt is the zero locus of this the polynomial ft inside the algebraic torus, and we take the intersection with the positive real space. So this is also a subset of the three-dimensional algebraic torus. And And what we integrate is the holomorphic volume form, and in this case, it's given by the divided by DFT. CT. So this gives the generator of the space of the holomorphic volume form CT. And the goal is to compute the asymptotics of period integral integration of this omega t along this cycle CT. And here is the idea. At first, we consider the following map. I like it as IT. It is a map from R3 to positive real space given by let's see, Y3 by this Y1 P to the Y2 P to the Y3. So this actually gives a bijection between this one is, and consider the free image of the cycle CT by this map IT. The point is that the first this R3 is the ambient space of trophical hypersurface, the V-trophet, and this positive real space is the where the cycle CT is sitting. And what we would like to do is compare this cycle and the V-trophet, the trophical hypersurface. And so in order to do that, we take the free image by this IT. And it turns out that the VT converges to the central sphere of V-trophet. The center sphere, what I mean by this is this part. There is a boundary of cube here, and actually this BT converges to this boundary of cube. This may look non-trivial claim, but we can actually check this by the similar argument as the one in the proof of the convergence for amoeba theorem. And since this is basically proved in similar manner, I'd like to skip to give giving the detail of the proof, but basically the idea are the same. So anyway, so we can compare the cycle over which integral consider the period integral and with the trophical hypersurface. And the next step is to decompose this and we think of the period integral as the integration over the VT of the pullback of the omega t by the IT, and we try to to compute this one. So then the second step is to decompose the integration domain BT into pieces. According to structure of the tropical hypersurface. For an example, so in this case, we BT is not exactly the same as the boundary of this cube, the central part, the sphere inside tropical hypersurface. But when T approaches 0, I mean, so sorry. As T approaches 0, then it converges to it. So let me write it just like a cube, boundary of cube. And we decompose this integration domain into pieces like this. And we compute the period integrals over each the divided region, and and at the end we take the sum of them to get the total value of the period integral. Sorry, the structure. That the boundary of cube. This part. Yeah. I drew it again here, but yeah, that's the same one. Yeah. Great. And let me pick 3. In the Calabi-Yau case, that is true. And it is expected that is the base space of the special SYZ vibration. And let me pick 3 region. This one, maybe, and this long and thin region, and this square region. Now it's time to apply the idea of tropical geometry for that picture. So one can simplify, as we did before. We can simplify the defining equation of the hypersurface. The T is equal to 0. Into like 1 is equal to E y1 to be safe, maybe E y1. Y1. So we have picked up the three regions, the yellow, red, and white. But on each region, we can simplify the equation as we did in before when maybe I have raised with you. So for example, on the yellow region, so there are only two leading terms, one and ty1, and so that is why. So this the one in on the left hand side are the that corresponds to that -1. So I moved -1 to the left hand side. This one is always one of the leading terms, and so ty1 is another leading term at the yellow region, and so I factor out the ty1, and other terms are can be ignorable. It ignorable, and so it is leading in this form, and we do the same thing for the red lesion and white lesions. In this case, it has more leading terms, but we factor out this ty1, and then they are written in this form, and one can compute these equations. Compute the asymptotics of the uh, 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 on each lesion approximately, and the and by summing them up. We obtain the total value. It turns out that we have we get the volume of the central sphere. The boundary, the cube sitting at the center of the figure of the tropical hypersurface times minus log t squared minus 24 z2 plus this one. Actually, it turns out that the local integration on each lesion gives us the volume of that lesion. And so in total, I mean, as the leading term of the period interval. And when we sum them up, we get as a leading term, we get the volume of the central sphere. And it also turns out that the red lesion, which is the long and thin rectangle, it also gives us the constant term, the zeta2. And so there are 12 edges on the boundary of cube, and on each edge, so there are two red lesions adjacent to it. And so in total, there are 24 red long and thin lesions, and each of them gives us the zeta2, and so that is why in total we get 24 zeta2, and so this is the result. And furthermore, we can also check that it is maybe I change the order. And this result is also rewritten in the following form. Am I correct? Yes. Times gamma x. Where x is an anti-canonical hypersurface of P1 cross P1 cross P1 with the canonical polarization. So when we want to interpret it as the formula in the gamma conjecture, then we suppose that E is the structure shape. So we have started with that reflexive polytope, but the polar dual polytope is exactly the three-dimensional reflexive cube, and the Calabi-Yau hypersurface corresponding to it is the anti-canonical hypersurface of the P1 cross P1 cross P1. As in the moment polytope of this is the cube. And so this is how they compute the asymptotic superiority intervals and confirm the gamma conjecture in this case. Okay, so yeah. Lastly, I would like to discuss the generalization of this result. Actually, we can also do the similar computation in the case where the hypersurface may not be Calabi-Yau. Yeah, so the claim of the main result is like similar computation. I mean, similar to their computation. Possible also in the case where the Newton polytope has more lattice points. So in the Calabi-Yau case, there is only one lattice point inside interior of the Newton polytope, but we can generalize the computation to the case where the Newton polytope has more lattice point in its interior. So for example, let's say we put additional point here, and so now the Newton polygon, it looks like, so it gets larger like this. Yes. So this is I mean, this is 2, 0, 0. So if you do like this, then the 1, 0, 0 is also a lattice point sitting inside the interior of the Newton polytope. And in this case, the hypersurface is no longer a Calabi-Yau hypersurface. But so let's say we put the additional term here, plus P cubed times Y1 squared. For example, and then the tropicalization also changes. We need to put 3, which comes from this power 3, and plus 2 times Y1. And graphical hypersurface range is like so yeah, now it has more chambers, like so so this the new vertex 200 corresponds to this region, and this 1, 0, 0 corresponds to this bounded chamber. We now have two bounded parts, this one and this one. And in this case, the let me yeah, here. So in this case, this space, the space of the holomorphic form on the hypersurface also gets bigger. Like we have actually another generator. Let me like the omega t prime. It turns out that this space now is generated by this omega t and t times y1 times omega t. So actually, this omega t corresponds to this the lattice point, the origin, and this new holomorphic form corresponds to this vertex. This is actually the how can I say general statement. Like the dimension of this space is actually the number of the lattice points sitting inside the interior of the Newton polytope, and we can actually take the generator of the homology group so that they correspond to one of the correspond to the lattice point inside the Newton polytope. And let me think about the period. So for example, we can compute the asymptotics of the integration of the positively real locus CT, sorry, along the positive real space CT of the omega t prime. So this is also a part of the information of period integrals or hot structures of the hypersurface. And so one of the highlight of the result of the computation is the following. Actually, it turns out that this only around that red facet are affected. What I mean by being effective is that basically we do the same computation. So we consider this BT as we did in the AG as done in AGIS, and we again decompose this period integration domain into pieces like this, and we compute the period integral for each region. But it turns out that the period integral for regions which is outside this facet are not approaches 0 when t approaches 0, and it turns out that the result of the computation is like the top term is given by the volume of that facet. times minus rho t squared minus 4 z2 cross epsilon. And this 4 comes from the number of edges in this red facet. And the reason why the integrals only allow the integrals over the regions outside this red facet is that actually this part Ty1 is dominant only around this new chamber, this one. And we are also integrating this omega prime over this cycle Bt, which converges to this cube. So what is effective is the integral over the around the intersection of this chamber and this chamber, which is the part which is close to this red facet. And actually, we can also see that the result of the period computation is also written in terms of in the form similar to the formula in the gamma conjecture. In this time, it is given by the homology pairing on the P1 cross P1 cross P1 and T minus omega times P1 gamma z plus epsilon. And where P1 is defined to be the divisor in this P1 times P1 plus P1 plus P1. And gamma 0 is relates to the gamma class. Or it is gamma 1 plus EI, gamma 1 plus DI. But this time, this is we think of this as a homology class of the toric variety, the P1 plus P1 plus P1. DIs are all toric devices. Only P1 minus P1 minus P1. Sorry, yes. Thank you. So now what is appearing in the result of period computation is a homology class of the toric variety, not the homology class of hypersurface. So it's the result seems a little bit different from the previous one, but this gamma 0 it's almost time. Yeah, actually, this class is the homology class of here, such that the restriction of this to the anti-canonical hypersurface of this toric variety is the gamma class of that hypersurface. So in that sense, it is almost like the gamma class of the variety. And so the conclusion is that we can calculate the asymptotic superior integral also in the case for the where the hypersurface may not be Calabi-Yau, and the result is also the result of the computation is also similar to the we can write the result so that it is similar to the gamma conjecture. We can actually also compute the period integral not only for the holomorphic volume form, but also the residue of the meromorphic form on the ambient space, which have fall along the hypersurface. But probably it's almost time, so I can talk about it. But yeah, I think that this is all, and thank you for your kind attention.
Thank you very much. Are there any questions? There is also a version of gamma conjecture for Fano varieties, but in terms of quantum cohomology. So yeah, how is this related to the the gamma conjecture that in your talk?
I don't know very well, but I think that it's also maybe might be possible to compute the like in the Fano case we consider the oscillatory integral, right? And so probably it may be possible to compute that in terms of tropical geometry, and but I'm not sure, and probably yeah, sorry, I can't answer for that.
And in your example, so you consider the CT you consider is rather special. So intersection of just this positive part of real cube. But what about the arbitrary Lagrangian cycle? So for arbitrary Lagrangian cycle, what is the recipe to?
So the general case, for the general cycle, it's probably hard to. At least I don't know how to do it, but actually we can also compute the so this is indeed, as you say, so this is just a positive real cycle, but we can also compute like we consider the varying the coefficient of the polynomial, then let's say so we vary the coefficient of the polynomial, then we get the family of the complex hypersurface parameterized by coefficients. But the positive real cycle is a cycle sitting in one member of the family. But we can actually compute the cycle obtained by transporting this positive real cycle continuously to other fiber. And so, and in general, there is non-trivial monodromy, and when it comes back, and then we get another, the cycle whose homology class is different from the original one. And so in that sense, we can compute period integrals for the more cycles, but probably it's not enough to give a complete description of the Hodge structure.
Okay, so are there more questions? So if not, then that's thanks Yuto again. So thank you very much.
Thank you for your kind attention.